Welcome back to AI Paper Podcasts. Today we're looking at something pretty fascinating. You see these AI models doing incredible things, right? Writing code, solving really tough math problems.
Yeah, things that feel like high-level intelligence.
Exactly. But then there are these other tasks, things we humans find almost intuitive, like navigating a space, reacting quickly to what we see, remembering where we need to go.
Things you do constantly, maybe even without thinking. And, funnily enough, skills you often pick up playing video games.
Right. And that gap between complex logic and what feels like basic intuition is really the heart of the paper we're discussing today. VideoGameBench. Can vision language models complete popular video games?
So this paper introduces a new benchmark, VideoGameBench. It tests these advanced vision language models, or VLMs, on 10 popular games from the 90s. We're talking Doom 2, Zelda, Pokemon Crystal, real classics.
And the core idea is simple. Can these VLMs, which handle language and visuals, actually use the human-like skills these games demand? Perception, spatial reasoning, memory.
And crucially, this benchmark is tough. Unlike other attempts, the VLM agent only gets the raw game screen. No text hints, no internal data, no special tools, just the pixels in real time.
Which brings us to the headline result, and it's pretty stark. Current state-of-the-art VLMs really struggle. A lot.
Yeah, the best one they tested, Gemini 2.5 Pro, completed less than 0.5%, like 0.48% of the games in real time. It's tiny.
Incredibly low. And they even tried removing the time pressure, pausing the game for the AI to think they called it VideoGameBench Light. Even then, performance only crawled up to about 1.6%.
So it's not just about thinking fast enough. It suggests a deeper issue, maybe with fundamental reasoning, planning, or just understanding the visual world in that context.
So that's our plan for this session. Unpack VideoGameBench, why they chose these games, how it works, dig into those results, and figure out what it tells us about where VLMs are today and where they might need to go.
Okay, so let's start with the games. Why the 90s? Game Boy, MS-DOS, what was the thinking there?
Well, the researchers argue these games are a step up from, say, old Atari games. They have more realistic 2D or early 3D graphics, different controllers, mouse, keyboard. It's a richer environment.
And they require more complex stuff, right? Not just reactions.
Definitely. Things like planning your route in Zelda, solving physics puzzles in The Incredible Machine, or managing combat strategy in Doom 2.
And the paper makes a really interesting point about human biases.
Yeah, that these games were built for humans. They rely on our kind of intuitive shortcuts for understanding the world. So they're a good test for whether AI can develop similar intuitions, similar inductive biases.
Okay, let's get into the setup. The rules of the game, so to speak. You mentioned the input is just the raw screen.
Just the raw pixels. And this is key. They deliberately excluded anything that might make it easier for the AI.
So no text descriptions popping up, no access to the game's internal memory.
None of that. No intermediate rewards telling it good job, no hints beyond the basic goal and controls. It's meant to be a pure test of visual understanding and action.
Which is quite different from some demos we've seen, like the Gemini Plays Pokemon one that got a lot of attention.
Exactly. Those often used extra tools, like maybe a pathfinding helper or something, to query the game state directly. VideoGameBench strips all that away. It wants to see what the VLM itself can figure out just by looking.
Makes sense. So how does the agent actually act in the game?
It generates language commands, things like press the A button, move mouse up, hold down arrow for 1 second. These get translated into the actual game inputs.
And there's some kind of agent framework wrapping the VLM?
Yeah, they call it VG agent. It uses a method kind of like React, where it observes the screen, thinks or reasons about what to do next, generating text for this, and then picks an action. It also has this sort of short-term memory, a scratch pad.
Okay, and how do they score progress? It's not just win or lose, right?
Right, it's more granular. Each game is broken down into checkpoints, completing a level, reaching a certain point. The score is the percentage based on the furthest checkpoint you reach.
How do they track that automatically?
It's quite clever. They basically scraped YouTube walkthroughs to get reference images for each checkpoint. Then they use perceptual hashing away to compare images to see if the agent's screen matches any of those checkpoint visuals.
Interesting. And they have development games and test games?
Yep, 13 dev games to tweak things and 10 test games. And 3 of those test games were kept secret, even from the model developers, to really test generalization.
Okay, now about VideoGameBench Lite, you mentioned latency.
Yeah, these big VLMs can take a little while to process an image and decide on an action. In a fast-paced game, the situation could change completely by the time the action actually happens.
So the action might be totally wrong for the new game state.
Exactly. So VideoGameBench Lite pauses the game emulator while the VLM is thinking. The game only runs when the agent executes its chosen action.
So it basically turns real-time games into turn-based ones.
Pretty much. It takes away the need for fast reactions and just focuses on the planning and reasoning part.
Got it. So let's dive into those results again, starting with the full real-time benchmark. The scores were not great.
Not great is putting it mildly. Table 2 in the paper lays it out. Across models like GPT-4o, Claude Sonnet, Gemini 2.5 Pro, Llama May 4, the scores are incredibly low. Gemini 2.5 Pro was top at 0.48% overall.
Wow. And for many games, across most models, it was just 0. They couldn't even clear the first hurdle.
Often, yeah. Take Pokemon Crystal. You mentioned the impressive demos before. Under these strict rules, Gemini 2.5 Pro scored 0%. GPT-4o got 0.9%. It really shows how much those tools and scaffolding were helping in previous showcases.
Okay, so what about VideoGameBench Lite? Taking away the time pressure must have helped.
It did help somewhat. Table 3 shows the scores went up. The best overall score climbed to 1.6% for Gemini 2.5 Pro. Some models that got 0 in real time managed to make a tiny bit of progress, especially in simpler games like Kirby's Dream Land.
But hang on, 1.6%, even with unlimited time to think about each frame, that's still really low?
That's the crucial point, isn't it? It strongly suggests the problem isn't just about reaction speed. There seems to be a more fundamental difficulty with understanding the visuals, planning ahead, or executing actions correctly, even when time isn't a factor.
Did they test even simpler things like basic controls?
They did. They had some practice games, really basic stuff. Clicking a target, dragging an object with a mouse, simple 2D maze navigation.
And how did the VLMs do there?
Surprisingly poorly, for the most part. Clicking was okay for some, but dragging and navigation were real struggles for many models. It suggests issues with even basic visual interpretation and mapping that to precise control.
And humans could do it fine using the same interface.
Yeah, they tested that. A human using the exact same setup, seeing the screen, typing commands into the VG agent, had no trouble with these simple tasks. So it wasn't just a clunky interface. It was the model struggling to use it effectively based on the visuals.
So why? Why are these incredibly powerful models, capable of amazing language feats and complex reasoning in other areas, finding it so hard to, say, walk through a door in Zelda? The paper looked into the failure modes, right?
Yes, they did some qualitative analysis looking at how the agents failed, and they found some interesting patterns. One they call the knowing-doing gap.
Knowing-doing gap? What's that?
It's where the VLM, in its internal thought process, the text it generates, actually states the correct thing to do. Like it might say, I need to move Link down to exit the room.
Okay, so it understands the goal.
It seems to, conceptually, but then it fails to execute it properly.
Yeah.
It might just press the down button repeatedly without moving Link over to the doorway first. Or it just gets stuck doing something else entirely. It knows what, but not how to translate that into the right sequence of actions in the visual environment.
Interesting. So a disconnect between understanding and action. What else?
Big problems with just processing the visual input correctly, misinterpreting what's actually on the screen.
Like seeing things that aren't there or missing things that are.
Kind of. They give an example from Doom 2 where Gemini 2.0 Flash kept shooting at an enemy that was already dead. The pixels of the dead enemy sprite were still there, and the model just didn't correctly interpret that it was no longer a threat.
Huh, okay.
Or another one in Zelda, where GPT-4o thought it had talked to an NPC just because Link was standing near them. It misinterpreted proximity as successful interaction.
So fundamental visual perception errors.
Seems like it. And then there's planning and memory. The agents really struggled to keep track of the game state, their objectives, or even where they were over time.
Right, you need memory to play these games. You can't just react to the immediate screen.
Exactly. And the models seemed unable to effectively use their memory scratchpad, or just lost track. They mentioned an agent in Doom 2 just walking back and forth between two zones, apparently forgetting its goal.
Okay.
And in Pokemon Crystal, GPT-4o would apparently forget it had already picked its starter Pokemon, or forget the main quest objective right after doing some simple task like exploring a building. Short-term goals seem to overwrite the long-term plan.
So if we circle back to the comparison with those tool-assisted demos, these problems, the knowing-doing gap, the visual misinterpretations, the poor planning and memory, these are likely the kinds of things those tools were compensating for.
That seems to be the implication. By forcing the VLMs to rely only on the raw pixels and their own internal reasoning, VideoGameBench really exposes these underlying weaknesses in core visual understanding and sequential decision-making in dynamic environments.
It makes sense. Using games to test AI isn't new, of course. We've seen amazing results from reinforcement learning, RL, in games like StarCraft or Dota.
True, but RL often works differently. It usually needs huge amounts of game-specific training, access to the game's internal state through special APIs, and carefully designed reward signals to learn.
Whereas the VLM approach is trying to leverage broad pre-training on language and vision to understand and act more like a human would, with less game-specific fine-tuning.
That's the hope, yeah, using those pre-trained priors. VideoGameBench is really trying to measure that specific ability. Can these models apply their general knowledge to a new, complex, visual task? Like playing a game, just based on seeing it.
And while there's other VLM work on games, this benchmark seems unique in its focus on complete, complex, real-time games using only raw visual input.
Right. It fills that gap. Now, the authors are fair about the limitations of their own work.
What did they point out?
Well, it's currently focused on 90s games and specific emulators. They acknowledge the need to broaden the range of games and platforms eventually.
Makes sense. Anything else?
The granularity of checkpoints could be finer in some games for more precise scoring.
Okay.
And there's always the lingering question of data contamination. Even with secret games, these are classics. It's hard to be 100% sure the models haven't encountered info or footage during their massive web pre-training, which could give them an unseen advantage.
Yeah, that's a tough one to eliminate completely with web-scale data. But despite the low scores now, the paper sees this as an important direction.
Absolutely.
Yeah.
They argue that making progress on this benchmark, improving how VLMs interpret raw visuals, navigate, plan, and act in real time based only on sight. Those are exactly the capabilities we need for real-world AI.
Like robots interacting with the physical world or drones navigating complex spaces.
Precisely. Those tasks require dealing with messy, dynamic visual input and making decisions, just like these games, arguably even more so.
Okay, so let's try and wrap this up. The main takeaway from the VideoGameBench paper seems pretty clear. Today's top VLMs, despite their strengths elsewhere, find it incredibly difficult to play these classic video games using only visual input.
Yeah, the benchmark effectively highlights this gap between abstract intelligence and the kind of intuitive perception, reasoning, memory, and real-time interaction that humans often take for granted.
And the analysis points to specific problems, like that knowing-doing gap, basic visual misinterpretations, and failures in planning and memory when the usual AI support structures are removed.
It really feels like a valuable, maybe sobering data point for the field. It pushes us to think beyond just scaling current approaches and consider what's missing for more robust general-purpose AI that can handle unstructured environments.
Which definitely leaves us, and you listening, with something to think about. What does this big difference, being brilliant at code but baffled by Pokemon Crystal, actually tell us about the kind of intelligence we're building?
And maybe more practically, if you're working in AI, what kinds of research directions are needed now? How do we bridge that knowing-doing gap and give these models the sort of common sense, intuitive understanding of the visual world that even a 90s video game demands?
It's a fundamental challenge, no doubt. Benchmarks like this are crucial for tracking whether we're making real progress.
Definitely food for thought. Thanks for digging into this paper with us today on AI Paper Podcasts.